Imaginary numbers exist on a dimension perpendicular to the real number line. Together, they form the complex plane. Watch what happens when we repeatedly multiply by I. Starting with 1, 1 times I is I times I is -1. By definition, -1 times I is -I, and -I times I is 1. We've come back to where we started, and if we keep multiplying by I, the point will keep rotating around. So when you're multiplying by I, what you're really doing is rotating by 90 degrees in the complex plane. Now, there's a function that repeatedly multiplies by I as you go down the x-axis, and that is e to the ix. It creates a spiral by essentially spreading out these rotations all along the x-axis. If you look at the real part of this spiral, it's a cosine wave. And if you look at the imaginary part, it's a sine wave. The two quintessential functions that describe waves are both contained in e to the ix.
I here denotes the square root of -1, called the imaginary unit. A and B are plain old real numbers, and this time, A is called the real part without the attachment of I, and B is the imaginary part, multiplying the imaginary unit. In other words, both real and imaginary parts are real. So we need two real numbers, A and B, to specify a complex number, which could naturally be put on a coordinate plane. So this point, having coordinates AB, corresponds to the complex number A plus BI. Because of this correspondence, we can represent all complex numbers on a plane called the complex plane. We usually denote a complex number as z, which is why it can also be called the z-plane. Now, since A is the real part, B is the imaginary part, the horizontal axis is the real axis, usually labeled as re-z. And the vertical axis is the imaginary axis, usually labeled as im-z. However, this is only one way of thinking about this point, the Cartesian way. There is another, the polar coordinates. R here specifies the distance from the origin, called the modulus, and denoted as the absolute value of z. Knowing the modulus is not enough because those on the circle all have the same modulus. So we also need to specify the angle theta made with the horizontal, called the argument, and denoted as arg of z. However, this can spark some arguments, pun very much intended. What if the point is down here? The modulus is perfectly fine, but for the argument, would you go clockwise, registering as a negative angle, or would you still go counterclockwise all the way around, registering as a positive angle? It really depends on your convention. I mean, technically, we can also add another 2 pi radian to it whenever we want. As long as you have a clear convention and stick to it, you are fine. In this case, the usual convention is to consider the negative argument. Essentially, we want the argument to be in the range -pi pi, so on the upper half plane, we get a positive argument, and on the lower half plane, we get a negative argument. The edge case is the negative real axis. In this case, we say that the argument is positive pi. More complex plane. This is the Cartesian way of representing complex numbers, and this is the polar way. Using simple trigonometry on the right-angled triangle, it is not difficult to see that A is r cosine theta and B is r sine theta. So apart from writing z as A plus BI, the other way is to use the modulus and the argument. As we'll see later, this bit can be further simplified. Anyway, this white box represents how we know A and B from r and theta, but what about the other way around? Using Pythagorean theorem, r can be quite easily found, and if we focus on the triangle, we can represent tangent theta as b over a, which seems to suggest that theta is arctan b over a, or is it? Remember that the argument is in the range -pi pi, but the arctangent function only ranges from -pi over 2 to positive pi over 2, so clearly something's wrong. But this isn't completely wrong though. If we are in the right half plane, then this is perfectly fine, because in this case, the range of theta matches exactly that of the arctangent function. But what's happening is that the ratio b over a is the same on this line, but still the same even for points on the opposite side. But instead of having the positive argument, we would have a negative one. Since the arguments differ by pi, in this case it should be the arctangent minus pi. Similarly, the ratio b over a is unchanged even on the other side of the line, and since this formula is perfectly fine in the fourth quadrant, and the argument should have been positive rather than negative, in the second quadrant, the argument should be the arctangent plus pi. Remember, we have the usual Cartesian way of representation in terms of its real and imaginary parts, but also the polar way of representation using the modulus and the argument. And this box is the interconversion between the two ways of representation. However, one thing before we close this chapter. Instead of thinking about the complex number as a point, we can also think of it as a vector emanating from the origin. And now we move on. Study more about complex numbers, but to actually derive it, it depends on how you define the exponential function. There will be 3 proofs based on 3 definitions in this video. The most common definition would be the power series. If this is how you define exponentials, this is the most classic way to prove the formula. We basically group every other term together. And based on the definition that I squared equals -1, we rewrite each bracket a little bit. And now we recognize that the first series is that of cosine theta and the second series is sine theta. And so we have e to the I theta equals cosine theta plus I sine theta. But this proof isn't that illuminating, because why do these series correspond to sines and cosines? To address this problem, people usually simply define sines and cosines using these series, which, well, rigorously speaking isn't a problem, but how do these series even relate to the geometric characterizations of sines and cosines? It isn't impossible, but that's a story for another time. So we turn to the second definition of the exponential, which uses its property related to differentiation. Namely, the derivative is simply I times itself, which is the basis of a nice visual proof. Before explaining this proof, we need a little fact, which is how we multiply a complex number by I. When a is multiplied by I, not too surprisingly, we get ai. And when bi is multiplied by I, we get -b because I squared equals -1. This means that the point AB is mapped to the point -BA by multiplication of I. But there is a really simple geometric illustration. This is the point AB, and after multiplying by I, we will get here, -BA. If we add the vectors and the angle, it might be a bit clearer what multiplication by I does. Yes, it is simply a counterclockwise rotation about the origin by a right angle. And so, we get onto the proof. First of all, we need to understand what this derivative means. E to the I theta can be thought of as your position on the complex plane. But the position changes with theta, so the changing positions create a trajectory. In this case, the trajectory isn't random, it is governed by this derivative equation, where the left-hand side denotes the velocity of a particle following the trajectory. The right side is the position vector, rotated anti-clockwise about the origin by a right angle. This relation, together with the fact that when theta is 0, the exponential is 1, allows us to determine the trajectory. So this is the complex plane. When theta is 0, it is 1, so the particle starts here. Since the velocity is perpendicular to the position vector, the initial velocity points upwards. So after a very small time, the velocity vector no longer points directly upwards because the position vector is no longer perfectly horizontal. In fact, as time goes on, the trajectory is exactly a unit circle. Throughout the trajectory, the position vector has length 1, and so the speed is 1 throughout the journey because the velocity is simply rotating the position vector with no stretching. So after time theta, the distance traveled is precisely theta, and so by definition of angles in radian, the argument of this point is exactly theta. Because this point is e to the I theta, we finally get that e to the I theta equals cosine theta plus I sine theta, Euler's formula. This amazing third proof, using the limit definition, but I'm going to put this off until later, where we develop an even better intuition of complex numbers. But let's consider the case where theta is pi, then cosine pi equals -1, and sine pi equals 0, and so e to the I pi equals -1. This is usually called Euler's identity, which is often considered the most beautiful equation.
Mathematics began as a way to quantify our world, to measure land, predict the motions of planets, and keep track of commerce. Then came a problem considered impossible. In 1494, Luca Pacioli, who is Leonardo da Vinci's math teacher, publishes Summa de Arithmetica, a comprehensive summary of all mathematics known in Renaissance Italy at the time. In it, there is a section on the cubic, any equation which today we would write as ax cubed plus bx squared plus cx plus d equals 0. People had been trying to find a general solution to the cubic for at least 4,000 years. But each ancient civilization that encountered it, the Babylonians, Greeks, Chinese, Indians, Egyptians, and Persians, they all came up empty-handed. Now this should be at least a little surprising, since without the x cubed term, the equation is simply a quadratic, b plus minus root b squared minus 4ac all over 2a. Mathematician Omar Khayyam identified 19 different cubic equations, again keeping all coefficients positive. He found numerical solutions to some of them by considering the intersections of shapes like hyperbolas and circles. But he fell short of his ultimate goal, a general solution to the cubic. He wrote, "Maybe one of those who will come after us will succeed in finding it." 400 years later and 4,000 kilometers away, the solution begins to take shape. Scipione del Ferro is a mathematics professor at the University of Bologna. Sometime around 1510, he finds a method to reliably solve depressed cubics. These are a subset of cubic equations with no x squared term. So what does he do after solving a problem that has stumped mathematicians for millennia? One considered impossible by Leonardo da Vinci's math teacher? He tells no one. See, being a mathematician in the 1500s is hard. Your job is constantly under threat from other mathematicians who can show up at any time and challenge you for your position. You can think of it like a math duel. Each participant submits a set of questions to the other, and the person who solves the most questions correctly gets the job, while the loser suffers public humiliation. As far as Del Ferro knows, no one else in the world can solve the depressed cubic, so by keeping his solution secret, he guarantees his own job security. On his deathbed in 1526 does he let it slip to his student Antonio Fior. Fior is not as talented a mathematician as his mentor, but he is young and ambitious. And after Del Ferro's death, he boasts about his own mathematical prowess, and specifically his ability to solve the depressed cubic. On February 12, 1535, Fior challenges mathematician Niccolò Fontana Tartaglia, who has recently moved to Fior's hometown of Venice. Niccolò Fontana is no stranger to adversity. As a kid, his face was cut open by a French soldier, leaving him with a stutter. That's why he's known as Tartaglia, which means stutterer in Italian. Growing up in poverty, Tartaglia is largely self-taught. He claws his way up through Italian society to become a respected mathematician. Now, all of that is at stake. As is the custom, in the challenge, Tartaglia gives a varied assortment of 30 problems to Fior. Fior gives 30 problems to Tartaglia, all of which are depressed cubics. Each mathematician has 40 days to solve the 30 problems they've been given. Fior can't solve a single problem. Tartaglia solves all 30. A challenge came. Tartaglia learns of Fior's claim to have solved the depressed cubic, but he's skeptical. I did not deem him capable of finding such a rule on his own, Tartaglia writes. But word was that a great mathematician had revealed the secret to Fior, which seems more plausible. So with the knowledge that a solution to the cubic is possible, and with his livelihood on the line, Tartaglia sets about solving the depressed cubic himself. To do it, he extends the idea of completing the square into 3 dimensions. Take the equation x cubed plus 9x equals 26. You can think of x cubed as the volume of a cube with sides of length x. And if you add a volume of 9x, you get 26. So just like with completing the square, we need to add onto the cube to increase its volume by 9x. Imagine extending 3 sides of this cube out a distance y, creating a new larger cube with sides of length, call it z. Z is just x plus y. The original cube has been padded out, and we can break up the additional volume into 7 shapes. There are 3 rectangular prisms with dimensions of x by y, and another 3 narrower prisms with dimensions of x by y. Plus, there's a cube with a volume y cubed. Tartaglia rearranges the 6 rectangular prisms into one block. One side has length 3y, the other has a length x plus y, which is z, and a height is x. So the volume of this shape is its base, 3yz, times its height, x. And Tartaglia realizes this volume can perfectly represent the 9x term in the equation if its base is equal to 9. So he sets 3yz equals 9. Putting the cube back together, you find we're missing the one small y cubed block. So we can complete the cube by adding y cubed to both sides of the equation. Now we have z cubed, the complete larger cube, equals 26 plus y cubed. We have 2 equations and 2 unknowns. Solving the first equation for z and substituting into the second, we get y to the 6 plus 26y cubed equals 27. At first glance, it seems like we're now worse off than when we started. The variable is now raised to the power of 6 instead of just 3. However, if you think of y cubed as a new variable, the equation is actually a quadratic. Equals 1, which means y equals 1. And z equals 3 over y, so z is 3. And since x plus y equals z, x must be equal to 2. Which is indeed a solution to the original equation. And with that, Tartaglia becomes the second human on the planet to solve the depressed cubic. Tartaglia's victory makes him something of a celebrity. Mathematicians are desperate to learn how he solved the cubic, especially Girolamo Cardano, a polymath based in Milan, manages to lure Tartaglia to Milan. And there, on March 25th, 1539, Tartaglia reveals his method, but only after forcing Cardano to swear a solemn oath not to tell anyone the method, not to publish it, and to write it only in cipher. Quote, Cardano is delighted and immediately starts playing around with Tartaglia's algorithm. But he has a loftier goal in mind, a solution to the full cubic equation including the x squared term. And amazingly, he discovers it. If you substitute for x minus b over 3a, then all the x squared terms cancel out. This is the way to turn any general cubic equation into a depressed cubic, which can then be solved by Tartaglia's formula. 42, Cardano travels to Bologna, and there he visits a mathematician who, on his deathbed, gave the solution to the depressed cubic to Antonio Fior. Cardano finds this solution in Del Ferro's old notebook, which is shared with him during the visit. This solution predates Tartaglia's by decades. So now, as Cardano sees it, he can publish the full solution to the cubic. 3 years later, Cardano publishes Ars Magna, the Great Art, an updated compendium of mathematics. Written in 5 years, may it last for 500. Writing letters to Cardano and CC's a good fraction of the mathematics community. And he has a point. François introduces the modern symbolic notation for algebra, ending the millennia-long tradition of math problems as drawings and wordy descriptions. Geometry is no longer the source of truth. René Descartes makes heavy use of the square roots of negatives, popularizing them as a result. introduces the letter I to represent the square root of -1. When combined with regular numbers, they form complex numbers. By letting go of what seems like the best description of reality, the geometry you can see and touch, you get a much more powerful and complete mathematics that can solve real problems. And it turns out Erwin Schrödinger is searching for a wave equation that governs the behavior of quantum particles, building on de Broglie's insight that matter consists of waves. He comes up with one of the most important and famous equations in all of physics, the Schrödinger equation. And featured prominently within it is I, the square root of -1. While mathematicians have grown accustomed to imaginary numbers, what is unpleasant here, and indeed directly to be objected to, is the use of complex numbers. The wave function psi is surely fundamentally a real function.